specific heat capacity. Take some water in a vessel and start heating it on a burner. Soon you will notice that bubbles begin to move upward. As the temperature is raised, the motion of water particles increases till it becomes turbulent as water starts boiling. We will now see what are the factors on which the quantity of heat required to raise the temperature of a substance depend. To quote the answer in the first step, heat a given quantity of water to raise its temperature by, say 20 degrees Celsius, and note the time taken. Again, take the same amount of water and raise its temperature by 40 degrees Celsius using the same source of heat, and again note the time taken. You will find it takes about twice the time and therefore double the quantity of heat required for rising twice the temperature of same amount of water. In the second step, now suppose you take double the amount of water and heat it. Using the same heating arrangement to raise the temperature by 20 degrees Celsius, you will find the time taken is again twice that required in the first step. In the third step, replace the water the same quantity of same oil and raise the temperature again by 20 degrees Celsius and note the time. You will find that time taken will be shorter and therefore the quantity of heat required would be less than that required by the same amount of water for the same rise in temperature. The above observations show that the quantity of heat required to warm a given substance depends on its mass m, the change in temperature delta T, and the nature of substance. The change in temperature of a substance when a given quantity of heat is absorbed or rejected by it is characterized by a quantity called the heat capacity of that substance. S equals to delta Q by delta T, where delta Q is the amount of heat supplied to the substance to change its temperature from T to T plus delta T. It can even be observed that if equal amount of heat is added to equal masses of different substances, the resulting temperature change will not be the same. It implies that every substance has a unique value for the amount of heat absorbed or rejected to change the temperature of unit mass of it by 1 unit. This quantity is referred to as the specific heat capacity of the substance. If delta Q stands for the amount of heat absorbed or rejected by a substance, S equals to S by M equals to delta Q upon M delta T, where M equals to mass, delta T equals to temperature change. The specific heat capacity is the property of the substance which determines the change in the temperature of the substance undergoing no phase change when a given quantity of heat is absorbed or rejected by it. It can also be defined as the amount of heat per unit mass absorbed or rejected by the substance to change its temperature by 1 unit. It depends on the nature of the substance and its temperature. The SI unit of specific heat capacity is Joule per kg Kelvin. If the amount of substance M is specified in terms of moles mu, we can define heat capacity per mole of the substance by C equals to S by mu equals to delta Q by mu delta T, where C is known as molar specific heat capacity of the substance. Like S, C also depends on the nature of the substance and its temperature. The SI unit of molar specific heat capacity is Joule per kg Kelvin. If the gas is held under constant pressure during the heat transfer, then it is called the molar specific heat capacity at constant pressure and is denoted by Cp. On the other hand, if the volume of the gas is maintained during the heat transfer, then the corresponding molar specific heat capacity is called molar specific heat capacity at constant volume and is denoted by CV. Specific heat capacity of some substance at room temperature and atmospheric pressure. Molar specific heat capacities of some gases. Note that you can note that water has the highest specific heat capacity compared to other substances. For this reason, water is used as a coolant in automobile radiators as well as a heater in hot water bags. Owing to its high specific heat capacity, the water warms up much more slowly than the land during summer, and consequently wind from the sea has a cooling effect.